A warm welcome to the 29th lecture on the subject of digital signal processing and its applications. In this lecture, we continue with the subject of FIR filter design by using the window approach. And we need to recapitulate a few ideas that we have learned in the couple of lectures that have passed on the subject of FIR filter design. The most important idea that we have seen in the previous lecture is the role of the spectrum of the window function. You see, it was a fundamental question why we should choose a window function other than the very simple option of a rectangular window. I mean, the rectangular window seems easy to do. Just retain a few samples and reject the rest from the impulse response. Why should we multiply that set of samples that are retained by some other sequence which has some quote unquote desirable properties? And what are those desirable properties? We have seen a little bit of this in the previous lecture, and we need now to substantiate by actually giving examples. But let us recapitulate what we've seen in the previous lecture. We've seen that the window spectrum has an effect on three things: the passband tolerance, the stop band tolerance, and the transition band or transition bandwidth. Now, in the window approach, we do not have separate control on the passband and the stop band tolerance. In fact, the passband and the stop band tolerance are equal in the windowed approach. And we've seen that in the previous lecture. The cause of passband and stop band tolerance is the area under the side lobe. The passband and stop band tolerance influenced by side lobe area. The reason for this is simple. The tolerance is caused by sidebands entering and leaving the ideal passband in the periodic convolution between the ideal DTFT or the ideal frequency response and the window spectrum. So, the passband is the region where the main lobe has completely entered the ideal passband, and now the side lobes are entering and leaving. The stop band is the region where the main lobe is completely outside. And the transition band is caused by the main lobe actually entering, and the whole process of the main lobe entering the ideal passband and ultimately going entirely inside is the cause of the transition band. And therefore, the main lobe width influences the transition band. We've seen that in the previous lecture. Transition band is influenced or is caused by, actually, influenced by the main lobe width. Now note, it is the main lobe width and the side lobe areas that play a role. The main lobe area has only a peripheral influence, and the side lobe widths again have only a peripheral influence. The influence of the main lobe area is only to determine the average height of the resultant passband. Now that is not a terribly important issue, because the height can be changed by simply multiplying all the coefficients by a constant. Now, even when we say the passband and or stopband tolerance is influenced by side lobe area, we should qualify this by writing relative side lobe area. That means side lobe area relative to main lobe area. So it is the relative side lobe area which really plays a role, not the absolute side lobe area. By relative side lobe area, we mean the ratio of the side lobe area to the main lobe area. Because the main lobe area is what determines the average height of the passband, and superposed on this height are the oscillations caused by the side lobe area. And if you multiply the whole set of the resultant impulse response coefficients by a constant, both of these are going to get multiplied by the same constant, so the relative side lobe area is not affected by multiplication by a constant. So you see, these two things play a very crucial role, and we have seen two examples in the previous lecture, the rectangular window and the triangular window. We saw that in the triangular window we have less relative. Now we didn't show that, but we gave an intuitive argument for it. We said that in the triangular window we definitely have a reduction of side lobe height, that we showed, relative side lobe height. But now I put a challenge before you. Show by reasonable approximation asymptotic approximation. By asymptotic approximation, I mean approximation as n tends to infinity, that the triangular window has less relative side lobe area than the rectangular window. Now the hint to solve this challenge is that you can treat the side lobes asymptotically like triangles, where the base is equal to the width of the side lobe and the height can be determined by an asymptotic approximation. So you may treat them very close to triangles and find out the area under the triangle, and then see how the area asymptotically changes as the length of the window grows to infinity. Now of course, as I told you, this comes with a cost. The cost is that the main lobe width expands, so it's not for free. Although the oscillations in the passband and stopband decrease, they do so at the cost of an increased main lobe width, which means a larger transition band. So the next point that we had seen in the previous lecture is that there is a compromise between main lobe width and relative side lobe area. Among windows. We also remark that this compromise, though generally present, can also be to some extent optimized, in the sense that one can do well on both fronts to an extent. Now, to what extent is a very, very basic and very fundamental question. How we determine how best we can do on both fronts together. There are two conflicting things happening here, the main lobe width and the side lobe area, relative side lobe area. But you see, there is a fundamental limit on how well you can do on both fronts together. And although I shall not go into the genesis of this fundamental limit or even try to explain it mathematically, I shall state the general idea behind this fundamental limit. This fundamental limit stems from something called the uncertainty principle. The fundamental limit on how well we can do on both fronts is essentially governed by what is called the uncertainty principle, governed by the uncertainty principle of signal processing. I shall just say a couple of sentences to put this in perspective, but to understand the relationship better or even to understand the principle better, one would need to take a higher level course on signal processing. The principle says that there is a basic conflict between the time and the frequency domain representation of a signal. So, if you try and narrow a signal down in time, the tendency for the signal is to expand in frequency, which of course we don't need a principle or uncertainty principle to understand, because we know that if you take the Fourier transform of a signal and then if you contract or expand the signal, there is a respective expansion or contraction in the Fourier transform. That is a basic property of the Fourier transform. So that does not require too much of exposure. What requires a much deeper understanding is that there is a fundamental limit on how narrow you can be in both domains. You can be arbitrarily narrow or broad in one domain. But to what extent can you narrow down in two domains together is what the uncertainty principle addresses. And in fact, it is very closely related to this whole question of how much you can narrow down the window in terms of main lobe width and side lobe area. Now, I shall not go entirely into the details here, safe to say that there is a relationship, and for those of you who are interested, you may want to look up more about the uncertainty principle or take a higher level course, or also try and reason out how this, in other words, expresses a basic conflict between expansivity in time and frequency. Anyway, with that background, we must now see some examples of window functions. We saw two in the previous lecture, but we must see more in this one. So, we will now look at a very common window called the Hahn window. We shall now take one by one expressions for different windows. So, in general, we shall specify a window as follows. We will specify a window to lie between k equal to minus n to plus n. And we will specify the window by the expression w of k. So, for example, the rectangular window is specified by wk equal to 1, and the Hahn window is specified by wk equal to half 1 plus cos 2 pi k by 2n. And we can easily see that at k equal to minus n, we have cos pi. So, this is 0. And so also at k equal to plus n and minus n. So, this becomes 0. And of course, what we are really doing is to place one whole cycle. You see, if you look at it, when k goes over an entire interval from minus capital N to plus capital N, you are running over a whole cycle of the cosine, taking you from an argument of minus pi to an argument of plus pi. And you are putting that whole cycle of a cosine on a constant, and therefore it will always be non-negative, but it will follow a cosinusoidal pattern. So, we can sketch the Hahn window for our convenience. As before, the best way to sketch is to draw the corresponding continuous function and then discretize it. So, you see, we have this cosinusoidal function here. bell shaped, if you want to call it that. The Hum envelope. So for each window we have an envelope, and the window is obtained by sampling the envelope. Now this idea of the envelope is important. You see, how you get the envelope is very easy. You get the envelope by replacing k by t. T becomes continuous. So in this expression you can think of replacing k by t. It gives you cos 2 pi t by 2n. So at t equal to minus n, you can say that anyway, of course, it takes the value 0 as before, and at plus n also it takes the value 0. And then of course at k equal to 0 it takes the value half, so it rises, and then so I'm sorry, at k equal to 0 it takes the value 1, I mean half into 1 plus 1. So this envelope of the window is important for all the windows, because when we are looking for an even length FIR filter, we need to do a little bit of work on this. You see, instead of, for an odd length window, of course you would include t equal to 0 among the samples, but when the window is of even length, you must include plus half and minus half among the samples, and then displace the other samples by 1. So you will get an equal number of samples on the positive side of t and on the negative side of t. So when you have an even length window, you need to draw the envelope and then sample it starting from plus half and minus half, and then displace by the integers. And the same is true for the ideal impulse response. We need to take the ideal impulse response, draw the envelope of the ideal impulse response, and then resample it starting from plus half and minus half, and then displace by 1. So for even length FIR filter design, we need to take this care. That's why the envelope is important. Now let's look at a few more envelopes. The Hamming window. By the way, Hum and Hamming are names of researchers in this field who have suggested this window. The Hamming window is described by Wk is equal to 0.54 plus 0.46 cos 2 pi k by 2n. And now of course you will wonder what sanctity these numbers have, 0.54 and 0.46. Except for the fact that they add to 1, they don't seem to have any other sanctity, and they really don't. You see, in general, one can talk about a generalized Hamming window, where you give this the value alpha, and therefore this becomes 1 minus alpha. That's the generalized Hamming window. And you see, the whole game in this Hamming window is to try, Hun window or the Hamming window, is to try and optimize between main lobe width and side lobe area. So that alpha is like a tuning parameter. It allows you to tune main lobe width and side lobe area. And of course you can't, take it arbitrarily. You can't use any value of alpha between 0 and 1. You would want, in fact, you would normally want it to remain at least reasonably positive all over the interval. But whatever it be, it's really a game of compromise between the main lobe width and the relative side lobe area. And again, the game is that when you go to a smoother function, now in general, the Hun or the Hamming windows do better than the triangular window in general, in terms of their main lobe width come side lobe, relative side lobe area performance. And the secret of this better performance is the fact that they have essentially a sinusoid, or you could say a zero frequency plus a first fundamental term. Now you can introduce one more term and perhaps introduce some more compromise, and that's what leads you to what is called the Blackman window. Again, Blackman is the name of another researcher. In the Blackman window, Wk is described by 0.42 plus 0.5 cos 2 pi k by 2n plus 0.08 cos 4 pi k by 2n. So essentially one has introduced a second harmonic term. And just as a good dish requires just the right proportions of different ingredients, a good window requires just the right proportion of different harmonics to achieve a good main lobe area and main lobe width and side lobe area compromise. And of course you could then conceive of introducing a little bit of a third harmonic and tuning it and so on. So window design is as much of an art as a science. You see, wherever there is no one unique answer, and different answers involve different kinds of compromises, the subject also acquires the form of an art, because there are beauties of various kinds. There is some kind of beauty in some window and some in some other. But a masterpiece among all these windows, there are several other windows, a masterpiece among these windows is what is called the Kaiser window. The Kaiser window is based on what are called the modified Bessel functions of the first kind and order 0. So let's denote it by I0x. And I0x is described essentially by its Taylor series. It's difficult to describe it in closed form. It looks temptingly like an expansion of e raised to the power of x, but it is not. This is a Taylor series expansion of the modified Bessel function of first kind and order 0. Now, just a little bit of background, you will recall that Bessel's functions arise as a solution to what is called the Bessel's differential equation. It's a very important equation in the whole field of differential equations. In fact, the Bessel's functions occur in many different contexts, seemingly unconnected. Of course, there are different kinds of Bessel's functions again. They occur in the context of communication, in the description of frequency modulation. And they also occur in other disciplines of engineering. Here, of course, you see they occur in window design. So they have some very interesting properties. Now, Kaiser studied this modified Bessel function, the Bessel function, for its spectral properties, and came out with the observation that it seemed to offer an excellent compromise between main lobe width and side lobe area. What I mean by that is, of course there is a fundamental limit. You can't do arbitrarily well on both, but you can probably do better on both fronts, and that also can be taken to a certain degree of achievement. And the Kaiser window is probably known to give some of the best results in terms of window design. And the beauty about the Kaiser window is that it has two tuning parameters. Of course, all windows have one tuning parameter. That is the length, right? So let's write that down. All windows have the tuning parameter given by the window length in fact the main lobe width is inversely proportional to n. So the more the length, the less the main lobe width. We saw that in the case of the rectangular and the triangular windows. But that is true of all windows. So you see, it's not correct to say that you cannot get as small a transition band as you want. You can get as small a transition band as you desire. The only problem is what is not affected by the window length is the relative side lobe area. And that is the tragedy of series approximations, sinusoidal series approximations. The relative side lobe area for a given window shape reaches an asymptotic non-zero limit and this is the origin of what is called the Gibbs phenomenon. Many of us have been exposed to the Gibbs phenomenon in sinusoidal series approximations. When we decompose a periodic function into its Fourier series expressions, what happens is the more and more the number of Fourier series terms that you retain in the expansion, the better and better are the discontinuities approximated. So you see, if you recall, if you have a square wave, and if you take one cycle of a square wave, and after all, what is an example of one cycle of a square wave? One period of the dTft. So if you take from minus pi to pi the ideal dTft, and then you look at the impulse response essentially as the Fourier series coefficients of this. Now that perspective is not difficult to see at all. Think for a minute. After all, if this be H ideal omega, what is the impulse response H ideal of n? H ideal of n is 1 by 2 pi integral from minus pi to pi H ideal omega e raised to the power j omega n d omega. So effectively these are like the Fourier series coefficients of this periodic dTft on the variable omega. That's another perspective on the impulse response. The impulse response is like a Fourier series expansion of the periodic dTft. Now we are looking at it the other way. All this while we thought of the dTft as a consequence of the impulse response. Now we are thinking of the impulse response as arising from the dTft. And that is not unreasonable because it is the ideal that we know in the frequency domain, and we want to find out the impulse response coefficients that should give us that ideal. And that process of finding the ideal impulse response is akin, or in fact is identical to a Fourier series expansion. And when we truncate this impulse response, what we are effectively doing is to truncate the Fourier series of that periodic function. And that's what leads us to what is traditionally understood as a Gibbs phenomenon. So what happens is, on the same, you see, you have, what happens is the more and more Fourier series coefficients you retain, you have this oscillation here, you get more oscillations as you approach discontinuity, then you get a rise, and then you get the largest oscillations here, and then you get smaller ones in between, you get larger and larger oscillations, and then again a drop, and then the largest oscillations, and finally it reaches a steady situation. And Gibbs phenomenon says that this oscillation does not reduce no matter how large you make the length. All that happens is that these oscillations get confined to the boundary near the discontinuity. But the magnitude, the height of those oscillations reaches an asymptotic limit. You cannot go below a certain value for the rectangular window. But of course you could go below that value if you took a different window, but of course at the cost of the transition bandwidth. So what I am trying to emphasize is that, once again let me say it very clearly, you see all windows have the tuning parameter given by the window length n. So all windows can give you as small a transition band as you desire. But what they cannot, once you have chosen a window, you have doomed the maximum deviation in the pass band and stop band. So the tolerance of the pass band and the stop band cannot be influenced beyond the point. You can influence the transition band, but you cannot influence the tolerance. And unfortunately the pass band and stop band tolerances are equal, or fortunately if you want to call it. Whatever it is, now the Kaiser window allows you one more tuning parameter, and that is like a shape parameter. So you see, as you see, it is the shape which gives you this maximum deviation, relative side lobe area. So it helps you control the shape. And the shape parameter allows you a tolerance between the main lobe width and relative side lobe area. So this Kaiser window is described by Wk is equal to I0 beta n square root, that's a complicated expression, but let's not bother too much about it, square root 1 minus k by n the whole squared divided by I0 beta n, with beta always greater than 0. So beta goes from 0 to infinity. And of course we have written the expression for I0 before. It's the modified Bessel function of first kind and order 0 in x. Now of course it is very easy to see that beta equal to 0 corresponds to the rectangular window. Beta is what is called a shape parameter. So the windows take different shapes. Now of course you must not forget that this window is described only between minus capital N and plus capital N. The modified Bessel functions of course last for all values of the variable. But this window is defined only between minus capital N and plus capital N. That is to be understood. And of course you can then draw the envelope of the window and then you could resample it to get the even length window. So the Kaiser window is in some sense an optimal in this game of compromise between the main lobe width and side lobe area. It was studied in depth by the mathematician Kaiser. And now typically it's the Kaiser window which is used when one uses FIR filter design with windows. And in fact, in the assignment that all of you would do to design the FIR filter using the window approach, you would use the Kaiser window. Now, how one chooses the shape parameter and the length is only by empirical experiments that have been done by Kaiser and other researchers. There is no closed form for choice. And what I shall do is to put down certain guidelines, so to speak, for the choice of length. The empirical design equations for the Kaiser window. You see, what we are assuming here is that we will take the case of the low pass filter, but a very similar kind of argument can be used for other kinds of filters. So of course you have pi here, you have omega s there, you have omega p. This is 1 plus delta up there and 1 minus delta down here, and delta down here, plus delta, and if you like, we can call it minus. So the response is between plus delta and minus delta, and 1 minus delta and 1 plus delta. Now notice that the pass band and the stop band tolerances are the same. We have no choice on that front. So the empirical design equations are as follows. The steps are: define delta omega t, or the transition bandwidth, to be omega s minus omega p. Define A to be essentially the logarithmic value of the tolerance, or the dB, decibel value of the tolerance. And define alpha to be beta times n. And therefore, the first step becomes the choice of n. So n is chosen according to 2n plus 1, that is essentially the window. Now I am talking about an odd length window here. So you see, if you want to design even length, then you can just choose one more or one less. After all, these are all empirical expressions. So 2n plus 1 is greater than or equal to 1 plus. Now these numbers have been arrived at by empirical considerations. 2.285 delta omega t. This is the guideline for the choice of n. To see more about these steps, one could look up any standard text on DSP. For example, one could look at the text by Oppenheim. Now, of course, we also need to determine the shape parameter. For the shape parameter, which we could either call alpha or beta. Alpha is of course equal to beta times n. So we will write an expression for alpha, and then you could of course correspondingly write an expression for beta. Alpha is equal to 0 for a less than 21. So you notice that alpha, the choice of alpha, is governed essentially only by the pass band tolerance or stop band tolerance, and that is to be expected because alpha, which is of course beta times n, the shape parameter, having chosen the length, then the choice of shape parameter has only to do with the tolerance. So alpha can be called the shape parameter here, beta times n, and what this means is that as long as a is less than 21, you could as well do with a rectangular window. Because beta equal to 0 or alpha equal to 0 essentially implies a rectangular window. Now if a is between 21 and 50, it doesn't matter, you can say less than or equal to. Then we choose this according to 0.5842. Again, all these are empirical. A minus 21 to the point 4 plus 0.07886 A minus 21. So it's the additional A above 21 which you are using in the expression. Yes, the question is, when a is less than 21, we are effectively saying the shape parameter is 0, and we are essentially saying the rectangular window does very well. What it means is the rectangular window gives you a tolerance which is less than 21 decibels. And finally, when A is greater than 50, the expression to be used is 0.1102 A minus 8.7. Alpha is equal to this. And of course, let's not forget that beta is equal to alpha by n. Now, the beauty is that, you see, for every kind of window, there is an equivalent alpha which gives you the same tolerance. What I mean by that is, take any window shape, triangular for example. Now the triangular window reaches an asymptotic limit in terms of its passband and stopband tolerance. What I mean by that is, after a while, after you keep increasing the length of the triangular window, you cannot reduce the passband and stopband tolerance beyond a certain point. That is called the asymptotic tolerance for that window, asymptotic delta for that window. The delta leads to an A, and the A leads to an alpha in the Kaiser window. So for every window, there is an equivalent alpha in the Kaiser window, which gives you that tolerance. The beauty is, for that alpha, of course you also have an n corresponding to, when you have a now the beauty is that, once you have chosen for the Kaiser, the beauty is the Kaiser window does better in terms of the transition bandwidth than most of the windows for that same alpha. So on a comparative platform, once you have chosen the alpha to match the tolerance in the passband and stopband, asymptotic tolerance in the passband and stopband for the window, the transition bandwidth is slightly reduced. So one can construct a table. For each window you can put down the way the transition band varies as a function of length. And one can put down an asymptotic tolerance. From the asymptotic tolerance you can find out the equivalent alpha. And then once you found the equivalent alpha, you can study how the transition bandwidth changes for the Kaiser window of that alpha with n. And the transition bandwidth does better for the Kaiser window than the original window. That is typically the case. That's interesting. That's why the Kaiser window is preferred. We'll take just one example to illustrate this. You see, for the Hun window, the peak relative side lobe amplitude, or the effective, so the peak error, let's not worry about the side lobe amplitude. The main lobe width is 4 pi by n. And the peak error in approximation, that is essentially the A that we have talked about, is 53. I'm sorry, this is 44 for the Hun window. I am essentially taking this data from a table. 53 actually happens to be for the Hamming window. The Hamming window and the Hun window have the same main lobe width. In fact, I can write it down here. Hun 44, 53 for Hamming. For the Hun window, if you take the equivalent Kaiser window with the same alpha. For the Hun window, the corresponding main lobe width or the transition width becomes 5.01 pi by 2n. And for the Hamming window, it becomes 6.27 pi by 2n. Now, of course, a greater A is better. A greater A means a smaller delta. You must understand this. So, greater A is better. So, in the sense of A, the Hamming window is better than the Hun window. In fact, that's why you see those funny numbers that were there, 0.54, 0.46, instead of half and half. But of course, better in the sense of tolerance and worse in the sense of the, well, actually equal in the sense of main lobe width. But Hamming is better in terms of tolerance. That's why the Hamming window would be preferred over the Hun window in a sense. The Hun window is easy to write, but it's not as good as the Hamming window in terms of its tolerance. But of course, you see in the corresponding Kaiser windows, of course, you see the compromise. The main lobe, the transition bandwidth increases a little bit. So as you go from beta equal to 0 to beta equal to infinity, it's a perpetual game. At the rectangular window, you have the very best transition width and the very worst tolerance. And as you go towards larger and larger beta, you get more and more transition bandwidth, but you of course do better and better in terms of tolerance. So this is how we design FIR filters using the Kaiser window approach. And now you are all equipped to complete your assignment, individual assignment on the design of filters, both IIR and FIR, with the specifications that you have been given. Yes, there's a question.
Sir, when you started the design, we moved from rectangular window to triangular and then cosine windows and so on. That means we are trying to go more and more smoother. And in Kaiser window, you said we are trying to approximate e raised to x. So why not use directly e raised to x as the window?
So the question is, it seemed like when we went from the rectangular to the triangular and then to the Hamming and then going further to the Kaiser, we were trying to make the function smoother and smoother. And we also remarked that when we looked at the Kaiser window, it seemed to temptingly resemble e raised to the power of x. So why not use an exponential itself? And the answer is that it's just a resemblance. The Taylor series is not really the expansion of an exponential. It looks like that. It looks temptingly like that. It's different because you have a square term, the x by 2, the whole to the power L divided by L factorial, the whole squared. So it's not quite an exponential. The exponential is not quite the optimal. It's really, so this modified Bessel function has been chosen by strategy. All right. So then we conclude today's lecture, and we'll see a little more about FIR filter design and some more things about FIR filters in the next lecture. Thank you.